All right. Where we left off last time was we were discussing a very simple model of a suspension where you have a spring and you have a damper attached to the body of a vehicle. What we did was we took this model and we created our own model, which looks like this, where this is now the ground. We set it at 0 for flat terrain. We then initiated a bump of height h that the vehicle is going to travel over. I think this one was S1, is that right?
Yep.
Okay, so this was S1, this is S2, D, and M for our mass. What we did was we set the height of the axle, which is here, we set that as X1. We set the height of the vehicle above where the mounts happened at X2. We had our 4 equations for heights. Height of axle was X1 minus 0. You had height of vehicle was X2 minus 0. You had the compression, well, you had the height of the axle above the bump. And that was X1 minus H. And then you had distance from vehicle to axle, which was X2 minus X1. Okay? So we're going to end up generating a bunch of different equations here just out of this. Okay, what we'll do is we're going to go ahead and take a force analysis of this axle, and then we'll take a force analysis of this vehicle, which I think I also did last time, but just playing catch up here. So here, you have the force of gravity acting downward on the mass. You have an upward force from spring 2, and you have an upward force from the damper. Both of those are supporting the vehicle. Okay, so that's the free body diagram just of the vehicle. For the axle, your free body diagram is you have a downward force, which equal and opposite in magnitude from the spring, a downward force from the damper, and an upward force from the bottom spring. Those are our 2 free body diagrams. Now we can figure out what each of these values are. Okay, what is the equation for the force through a viscous damper? What? Viscous damper. I gave you this equation, I think last time. Well, you know what? Let's do the easy ones first. What's the equation for a spring force? That's Kx, right? So I'm going to go ahead and say K times distance equals force through a spring, right? That's just the equation that we know. Okay, so what we have here is at static equilibrium, I don't remember who it was last class who pointed this out. Oh, this camera is so off angle. That's better. I don't remember who pointed this out last lecture, but whoever did, they did a really good job of noting it. This force has to carry the entire weight of the vehicle. It has to. Now, if there's any acceleration, then it will either be carrying more load or less load than the entire vehicle, depending on how the vehicle is accelerating. But in any case, at equilibrium, all of the weight of the vehicle is sitting on this spring and this spring. At equilibrium, there's no velocity. And because there's no velocity, there's no damping. So if x dot equals 0, Fd equals 0, because Fd is equal to Cx dot. So if there's no velocity, there can't be any damping force. So at equilibrium, all of the force is being transmitted through these two springs. Okay? We have this equation to show it. So our Fs2 is equal to K2 times what is the distance, what is the length of that spring? It is x2 minus x1. Woo, that's 1. Okay? Now I put that in brackets because we can't exactly just say, oh, you know, this is what the spring force is. This is the distance, the total length of the spring. This isn't the change in length of that spring. Okay, so yes, that is the length of what spring 2 is, but this is not the force. Otherwise, I mean, you get a bigger spring, all of a sudden you have a longer force. No, that's not really it. In reality, this is the current length. And this is the initial length. Okay? Where this value here is the initial height of, well, the initial length of the spring before it's compressed. Okay, now what this is referring to is if you were to pull the vehicle off the ground, the vehicle tire would drop to some certain length, and you would have some uncompressed distance, x2 to x1, to the bottom of the tire. Okay, that's basically what this is saying. This is going to be a constant. If you have to pull your vehicle off of the ground, you're going to get some constant distance between this and the axle. It's just what's going to happen. So we're going to go ahead and just call it a new variable because we can. If you want to leave it as x2 naught minus x1 naught, go ahead. It just means there's no force traveling through the system when that's measured. But I'm going to go ahead and I'm going to rewrite that as x2 minus x1 minus s2, or nope, sorry, LS2, where LS2 is just the uncompressed spring length. Okay, so if the spring is in compression, this number will be smaller than this number, which means it's pushing outward like this. It becomes a compressive force. If this, which at this point our arrows would be pointing the wrong direction, so really it should be a minus plus. Because we drew it in compression. If this goes further in compression, this number gets smaller, this number stays the same. So that's why I change that. Should have written it with these switched around. The way that this is written is if the spring goes in tension, the number is positive. If it goes in compression, it's negative. We drew ours in compression, so we have to switch those signs. Does that make sense? Just trying to make sure that we get a positive value when we're actually getting a positive value. Okay, so that's the spring force for FS2. This does have two variables in it, which that's kind of gross. But that's what we have to deal with. For FS1, FS1 equals K1 times, again, x1 minus 0, which I'm going to go ahead and say minus, because once again, we're drawing it in compression, plus, and I'm going to go ahead and just call this LS1, which is the uncompressed spring length. Okay, same thing as this. It's x1 0 minus the bottom of the tire height when it's not compressed. Your tire does have some amount of compression that occurs just by laying it on the ground and putting a vehicle on it. Okay? So we have this equation, we have this equation. Now we have to take this and do something with it. If both the axle and the vehicle are moving at the same speed vertically, are we going to have any damping force? But a damping force requires velocity. If it's moving, shouldn't there be a force? If my axle and my vehicle are both bouncing up, but they're staying at the same height relative to each other, shouldn't there be a damping force because there's a velocity? It's a trick question. That's why all of you are giving me that, I know you're tricking me look. You've had me for long enough. Dang it. In the reality, the only thing that causes a force is not the fact that it's moving. I mean, this thing's rotating around the sun at millions of miles an hour. It doesn't mean, gotta exert a force. Like, no. Plus, the world is rotating, and that itself is causing it to move at like a, whatever the circumference of the Earth is divided by the daytime hours. It's moving. We can't stop this from moving. But just because it's moving doesn't mean it's got some kind of force in it. The only thing that's going to create force is when the two ends of the damper have a different velocity. If there's a velocity of whether the damper is compressing or extending. Okay? If the two ends of the damper have a different velocity, then there's a force. The purpose of the damper is to prevent the two ends of it from moving at a different speed. So if they're both bouncing up and down, but they're at the same height, the relative distance between them doesn't change, and the relative speed is 0. So the only way we're going to have any kind of velocity between these is if the distance between them is changing over time, which is the definition of speed. When you have a distance change over time. If distance doesn't change, you have no speed. Doesn't matter how much time it takes. Okay, so third equation, make sure I'm not writing off the edge of the board here. The third equation that we have is our force in our damper is going to be equal to C times the speed, the relative speed between x1 and x2. So you could say, just for simplicity's sake, we're going to say delta x2 minus x1 over delta t, which that's the derivative of the change in time. Right? Or you could make it be d, right, instead of using a delta, which is a very math heavy symbol. Right? So now the change in x2 minus x1 over time, right? This is the speed. The distance we have is x2 minus x1. We can call that x3. x3 equals x2 minus x1, which is the length of this damper. We're looking for dx3 dt, which happens to have this equation. What happens when you take the derivative of two independent functions? Does x2, which is the height of the vehicle, is that a function of x1? It's actually a function of time. You can't derive x2 in terms of x1. So this is not true, which means x2 is equal to x2 of t. It's a time derivative function. x1 is equal to x1 of t. You can correlate them with time, but it itself is not actually a function of the axle. The axle can move independently, and it will change the forces that are being exerted on x2, but that's it. That's the only relationship it has. So what you have here is two independent variables that are both being derived, and this ends up being c times dx2 dt minus dx1 dt. What is dx2 dt? What's the derivative of displacement? It's displacement is a time varying function. What is the derivative of a time varying displacement function? Displacement is position. What's the derivative of position with time? You said it, just say it louder.
Velocity.
It's velocity. This is x2 dot. Huh? Nope, it's a derivative. The integral of velocity is displacement. Just like the integral of acceleration is velocity. So this is x2 dot minus x1 dot.
I think we all thought it was velocity was the integral of displacement.
It's been a while.
It's been
It's been a while. It happens. But that's why I'm asking these questions, trying to make you knock the rust off of your gears.
You said that, I was like, wait, what?
Yeah.
I was thinking it was like,
So now these are our three force equations. We've written them in terms of the force is now a function of the displacement. The displacement is a function of time. It has to be, or else we can't take the derivative with time. Okay, so force is a function of displacement. Displacement is a function of time. We can now take these and put these all together to come up with our equations. All right, so I'm looking at just free body diagram 1 and free body diagram 2. Okay, from free body diagram 1, we only have y directional forces. It does make it simpler. You want to add x directional forces, be my guest. No, she was not.
what?
Why are you commenting on my you're right here.
Huh? No, I opened up the YouTube and I put that issue with Untitled, so we check the comments.
Thank you.
You're welcome. It's less funny now that I have to explain it.
Well, nobody else is watching the live stream in here. Oh, man. Okay. All right. So from the first free body diagram, the sum of the forces in the y direction are equal to, we have three forces, but we're also going to include a fourth force, which is the inertial force, because otherwise it's equal to ma. Okay, so we'll take this FMA, and we got, we'll say this direction is upward for y, and then what we have is FS2 plus FD minus FG minus FMA is equal to 0. Okay, we have an equation for each one of these. What is the equation for FS2? Okay, what is FD?
C times x dot 2 minus x dot 1.
Okay. What is FG? Ryan? Dang it. Like I said, I can only tell you apart by your smiles. All right, Josh. What is the force of gravity?
Mass times gravity.
Mass times gravity. Okay, and this is a minus. And what is the inertial force? FMA. Ryan. Did you watch the lecture last time?
Yeah.
Okay. It's in the notes. FMA was written as,
Mass times acceleration.
it's mass times the acceleration, which here, the acceleration of this mass, the position is x2, so the velocity of this is x2 dot, and the acceleration of this is x2 double dot. Okay? So it's mx2 double dot. And this is equal to 0. So that's ugly. We can clean this up. And we should clean this up. But you know what? We're not going to because we've got to keep moving in class. We'll talk about how to solve this later, but this is the equation. If you just say, okay, I derive the equation, and you write this, if your question is to derive the equation of motion for the system, that's it. All right, but now we can go to free body diagram 2, because this is only half of the system. Sum of the force in the y direction is equal to what? What?
FS1 minus FS2 minus FD.
FS1 minus FS2 minus FD. And that's equal to 0. We're assuming that the axle is effectively massless because it is a significantly lower mass than the vehicle. Is that an accurate depiction? No. But is it going to change our math much? Oh, heck yes. It's going to make everything a lot easier. Having a second inertial force just means, ugh, blech. So, we take this system. What is the equation for FS1?
K1
K1 times,
x1 minus 0 plus ls1.
I'm just going to simplify that a little bit, ls1 minus x1. But yes, that's right. FS2 is that equation, which I'll just write again. K2 times negative x2 minus x1 plus ls2, and then minus the damping force, which is c times x2 dot minus x1 dot. And that is equal to 0. These are your two equations of motion. Solving these two equations, you only have two variables. x1 and x2. That's it. How to solve those is differential equations, which is gross, but that's all it is. It's just doing differential equations. Okay? So yes, these two equations are gross, but getting to this point is pretty straightforward. Just using what you know about statics. All right, we're going to move on from linear systems like this to a little bit more, well, other applications. I would say it's more challenging, but for some people actually think in rotational systems, which is pretty fantastic. I wish I was one of those people. I am not one of those people, but I wish I was. I think in linear translation. That makes sense to me. Okay, so the next system we're going to discuss is rotational systems. Okay, in a rotational system, you have the exact same components. You have inertial forces, you have capacitive or spring forces, and you have dissipative forces or resistive forces. Okay? In a linear system, the inertial forces occurs because everything has mass. Moving that mass means you have to apply some amount of force to it just to move the mass. In a rotational system, what we're dealing with is here, this is some kind of wheel we have that's spinning. And this has some mass, but if all the mass is centered right here around the center of the wheel, it's easier to spin. And if all the mass is centered around the outside of the wheel, it's harder to spin. Per the same mass of wheel, the distribution of weight in that wheel is going to change how hard it is to spin the system. It's no coincidence that a bike tire has all of its mass distributed around the rim. Okay, very, very thin spokes. The reason for that is to try to maximize its rotational inertia, which by doing so actually gives the bike a lot more stability. Okay, so the inertial element of this, what makes the rotation difficult is the rotational inertia, the mass moment inertia. Okay? So that's what generates the inertial force. In the translational system, that force is generated by only a mass. Here, it also depends on the distance, so somebody calculates the mass moment of inertia. Mass moment of inertia, unlike mass, is a lot easier to change for a system. Let's say we have a wheel that spins where you have 3 propeller blades like this of some mass m each that are spinning. Okay? It has some inertial mass I. If I bring these 3 propeller blades and I collapse them in, it's going to change your mass moment of inertia. That's it. You aren't changing the mass, but changing the geometry of the system adjusts the mass moment of inertia, and it does allow you to change the I value without having to lose anything. In a translational system, you can't do that. So it's an interesting combination of how a rotational system can be easier. Are you just eating hot dogs?
No, they're like little salami.
Oh, with the cheese inside?
Inside.
Oh, that is amazing. Well, it's like, you're just going to start eating hot dogs in class. Like,
And just scarf down some glizzies.
like that's me in college. Great. And I'm really hungry. Dang it.
Sorry. Are those glizzy?
It's all right. I'll forgive you this time. You got to take care of yourself, man. So the inertial force that is generated by this, unlike the last one, which is pretty much fixed at m times x double dot, this can change. You have the ability to adjust this in a system. Now, it would require some kind of an actuator to hold it at a certain place or bring it in. But you have the ability now to adjust the inertial force, which is kind of cool. It gives you an extra design element. Not a lot of people do this because it makes the math gross. But it is really sweet. The implications of this. You also have a resistive or dissipative force. Last one, it was a damper, provided friction. Here, it's basically a rotational damper. It's also friction. Mechanical systems are prone to friction, so this is not anything exciting. And again, you have your capacitive force. Capacitive force stores energy. It's also a spring. It's just a torsional spring. So the mechanical analog between a rotational system and a translational system, while the systems look entirely different, the components themselves are almost identical. Okay, so let's take right now, let's say we have a really long axle, and we have a wheel on the end of this axle, like this, and we're just going to rotate this axle. Maybe we got a bearing here, maybe we got a bearing here, and then maybe we got a gear on this end, and we got a wheel here. Okay, this system will have all three of these forces associated with it. And that's kind of gross because I didn't draw a spring on that.
True.
And I didn't draw a damper either. Okay, so this system looks significantly different than the suspension system I just drew, but it has all three of these components. All right, rather than looking at displacement in a translational system, we're dealing with x, which is displacement. And we're dealing with f, which is the forcing function. Or how force is distributed through an object. Okay? In a rotational system, instead of dealing with x as displacement, we're dealing with theta, which is a rotational displacement, or an angle. Okay? The derivative of x is velocity. The derivative of theta is angular velocity, omega. The double derivative of x is acceleration. The double derivative of theta is the angular acceleration. You just throw angular on here. You can call this angular displacement. Just displacement. You just throw an angular on the front of this, and suddenly it's rotational. You give it a different symbol. For the forcing function, instead of doing this, we're now dealing with moments. Although in this system specifically, we're talking about moments that are acting about the center axis of rotation of the system. In order for this to be a rotation system, it has to have some central axis. And because it is a moment where all of the moments occur about a central axis, these are all torques. Which is a moment occurring about rotational axis. Okay? Force times distance. Anybody know what that is? A force times a distance is the energy that is contained in a spring. It is a formula for energy. You have to divide that by 2. The distance multiplied by the torque is the energy contained in a rotational system. We're dealing with identical things. Okay? Take the time derivative of this, it's power. Take the time derivative of these two multiplied by each other, it's power. So all of these equations are linked by the fact that they all go back to energy. I mentioned this last time. This is very much a study of energy. But this is all the equations, and the energy never even shows up in the math. But we could figure out energy very easily from this just by multiplying these two together. That's it. You can figure out the amount of energy that is being dissipated by the damper. You can figure out the amount of energy that's being stored in the axle by multiplying this torque by the amount of distance that it rotates. All right, so I said that that system has the same components, has a dissipative force in there, has a capacitive force in there. I got to make good, and I got to explain how that works. So I will do that. Okay, first of all, this wheel has some mass m. Okay? Rotating the wheel provides some inertial resistance. In a translational system, that inertial force was mass times acceleration. In a rotational system, that torque, because that's the rotational analog here, is going to be equal to the mass moment of inertia times the angular acceleration, which the angular acceleration is equal to I theta double dot. It's the second derivative with time of the angular displacement of the wheel. Okay? If the wheel is not accelerating, if the velocity is not changing, you will have no inertial force. Okay? So, one down, got the inertial force. For this system, what is the capacitive force? So here we have kinetic energy that's being stored in the wheel. Kinetic energy is associated with your inertial force. Okay? Changing that kinetic energy requires force, or torque in this case. Okay? So that's one energy. Dissipative energy for the last one was a damper. So the wheel is rotating on bearings. The bearings support it, the bearings hold it up. The bearings are ultimately what stabilize it. The bearings serve as boundary forces that prevent that axle from moving in any linear direction. Now, these bearings usually don't prevent the axle from pulling out. You can just pull the axle out. You may have a set pin in there that prevents you from pulling it out. But most bearings, well, a lot of bearings don't. It does make it a lot simpler. It reduces stress. Anyways, it's rotating on the bearings, but the bearings themselves are going to have some frictional losses. Okay, when you ride in your car and you pull your foot off of the accelerator and maybe you're in neutral, you shut your car off, your car will eventually come to a stop. And all that energy that your car had in moving forward is transferred into heat through the bearings, through the gears, through any mechanical components that move anytime your car moves. There are frictional losses. Okay? Rotating the axle causes some heat to be generated.
Obviously, there's no frictional force between the wheel and the ground.
If there is, I mean, you can have in a perfectly rigid wheel that has frictional force on the ground, there is no heat dissipated. So weird. Having a tire, there is some movement there between the tire and the ground. It's rubbing, which that actually does create friction. But for this, we're going to assume that there is no contact between the wheel and the ground. At least no dissipated energy. Otherwise, that would contribute to this overall frictional force. Okay, here, so this is T inertial. This is T dissipate, which just means that it's a torque created by transferal of energy from rotational to heat. This is going to be equal to C theta dot, where theta dot is your omega, which is your angular velocity. So if it's not moving, if it's not rotating at all, you're not losing anything to heat. It's not a heater that just suddenly turns on. Okay, if it moves though, there is some energy lost in heat. And that energy comes in the form of a torque that is actually exerted, that constantly sucks energy, siphons energy out of your system. Okay, so that's the damper section of this. You can actually put dampers inside of your wheels. You can put brakes on your wheels. All a brake does is it dissipates energy in that way. Now, a lot of brakes are dry contact. As I mentioned last time, dry contact equations are a little bit different. A lot of times they are not velocity dependent. We're not getting into that kind of math. It's just not as pretty as this. So we're only focusing on what is viscous damping here. But you can have dissipative energy that comes in the forms of braking, or maybe this axle's doing other things to generate heat. The equations for those are different. Okay, lastly, the axle itself deforms under torque. If I grab onto this marker and I twist it, you won't see it, I won't see it, but there is some amount of deformation that happens where the angle on this end is no longer equal to the angle on this end. Okay? You want to use the example of a garage spring. A garage spring has lines that go down it like this. You twist your garage spring one full revolution, and your spring now looks like this. It shows one full revolution there. Okay? Creating, by twisting the two ends relative to each other, you get a different angle on both sides of your tube. Now, if your tube is very strong, that angle is going to be very small. But there is energy that is stored because this tube deforms, this tube rotates, because there's torque on that tube. You cannot apply a force to a material without that material deforming. You cannot apply a torque to a material without that material deforming. And here, the torque in this axle is going to be storing energy. Turns out the longer the axle, the more energy ends up getting stored because it has to rotate further. Because the axle itself deforms, it behaves like a spring. If you ever walked across soft carpet deforms under your feet, it acts as a spring. Everything when you apply a force or a torque to it behaves like a spring. Doesn't matter if it's concrete, doesn't matter if it's steel. You walk across a steel I-beam, it is behaving like a spring. It is absorbing your energy, and it is absorbing it through deformation of the material, which is the definition of a spring. Force times distance. Well, you have some force that you're applying to a material, it deforms some distance, that is energy. Now, we don't weigh enough, and a lot of the materials we use don't weigh enough to create visible deformations of materials. If you're walking across the ground and you can see the concrete moving underneath your feet, either one, it's wet concrete, or two, you are smashing the concrete. Okay? And you might need to either get a weight loss plan or turn into the Hulk or something. When you apply a torque, the material itself deforms. And when that happens, your capacitive torque occurs when you have some spring constant multiplied by some angular displacement. This equation looks very similar to K times X, which is the equation for our spring. It's just instead of using X, we're now using theta. This equation looks a whole lot like Cx dot. This equation looks a whole lot like MA. That is not unintentional. The formulas for these are identical. As soon as you understand this, now when we apply some torque through the gear, let's say we have some forcing function T that is driving all of this. When we do the sum of the moments about, let's say this is maybe the x-axis, which is just the x-axis. I don't know why I wrote that twice. This is equal to the applied torque minus your inertial torque minus your dissipative torque minus your capacitive torque. And that's equal to 0. The energy that's being absorbed by the material deforming, or if you actually have a spring, the energy that's being absorbed by the spring. The energy that's being absorbed by the bearings, or you can actually have a rotational damper too. If you want something to slow down faster, you would want to have this be a larger value. So you would actually get a bigger damper. And then lastly, your inertial, which is just the fact that you have a mass rotating at a distance. All of these have to equal equilibrium. Now, in equilibrium, at a constant speed, what is the value of your inertial torque?
0.
Why is it 0?
There's no acceleration.
There's no acceleration. Because you're at a constant speed, the derivative of a constant is 0. So at a constant speed, you're driving at a constant speed down the highway. You are not experiencing inertial changes in your wheels, in your vehicle, nothing. Driving at a constant speed, you have no inertial force. This goes away. At a constant speed, with a constant torque, this is also constant. And this ends up being, well, it ends up being 0 because you're not changing that spring value. You set something on a spring and you don't move it, that spring doesn't absorb anything. Okay? The spring has already reached its maximum loading when it's at equilibrium. This is also 0. At equilibrium, traveling at a constant speed, all of the torque you're putting into the system is going into heat. Okay, and we can plug these formulas in to that equation. You'll get very similar equations to what we just dealt with. I had a bigger system. The math is the same. Let's say instead of doing this, I got 20 minutes before the end of class. Let's say instead of doing a system that looks like this, now let's actually put in a spring and a damper, okay? That system, it does still have the same math. These components are going to be small, very small, intentionally so. But they're still there. You can't ignore them. Well, you can ignore them if there's a spring in the system or if they're very negligible. You can't ignore them. You can treat it like it's a rigid axle. And all of a sudden, then this goes away. In a very short axle, this isn't going to absorb a lot of energy. I promise you can guarantee you can ignore that. It's not going to absorb a lot of energy. Okay? In near perfect bearings, you can try to ignore that. And then the torque that you're exerting on that axle is going to be equal to the amount of speed change that occurs here. Okay? That's it. But in a more complex system, let's say now I've got a rotating wheel again, maybe this is a flywheel, and I have some kind of a torsional spring. It's mounted to this axle. Maybe the torsional spring actually carries torque from one axle to another, so it kind of serves as a shock absorber, so to speak. And what this does is this transfers torque from one axle to the other. Okay? So maybe they're both riding on some other, but it is actually the torsional spring that transfers torque from one axle to the other. Without that torsional spring, this axle spins independently of this one. Okay? And then let's say we put some kind of a damper system on here. It's a fluid viscous damping system. The more that fluid has to rotate, maybe this viscous damper is powering a hydraulic system, whereby forcing that fluid to move forces fluid to move through the hydraulic system. You can do that. It doesn't have to go towards heat just where it just all burns up in heat right here.